Okay, so let's talk about current density. What's that, you say? Why we need to talk about such a thing? Well, let's see what goes on here. So let's first draw a large view of a wire with current in it. So here's going to be our usual view of the wire. It's like a cylinder. That's going to say length capital L. And of course, we're going to be dealing with conventional currents. We're imagining it's the flow of protons, even though we know of our heart of hearts, it's electrons that flow. So let's say we want the protons to flow from the left side to the right side. So I want you to label the two ends of the wire. Where's going to be a high potential? Where's going to be a low potential? Sure, of course, the protons are going to flow from high to low, so the left side will be the high potential, the right side will be the low potential. So to create that, we'll need to attach a voltage source, a battery here. So let's run some wires from either end, and the gap in the middle is where the battery is going to go. So just go ahead and draw the orientation of the battery to create this potential difference. Of course, long line on the left, short line on the right, high potential, low potential. Great. So now we have a flow charge going through here. Now, we talked a lot about different analogies. And remember, when charges are flowing through, it is chaos inside. The charges are going all over the place. It would be really nice if the charges flowed very nicely from left to right, nicely. And, you know, if we take the grand scheme view of it, yes, they do flow from left to right. We talk about the drift velocity of that happening. But even so, there may be places where the currents are different. If you can imagine like sectioning off the wire into like a little bit of a current there, and a current there, and a current there, and a current there, it's possible that all the currents will be the same anywhere inside the wire. It's also possible that it's not. And to account for this, we're going to define this idea of current density, like the concentration of currents, which may or may not be uniform throughout the conductor. And so here's going to be our definition. Capital J will stand for current density, and it's going to be current over area, where area is the cross-sectional area of the wire. So we'll define capital J as current density. We're going to leave a little bit of room here. We're going to write a little bit more about that in just a little bit. Let's consider whether or not this is vector or scalar. So we got current. Is that vector or scalar? Yeah, it is scalar. Remember, even though we often draw arrows on the circuits to show which way the charges are moving, those really aren't vector arrows. Those are more like velocity arrows. In fact, they're kind of like drift velocity arrows. Current itself really is a scalar quantity. Okay, what about area? Well, we've seen area as a vector before, so you know what? It is actually going to be an area here, which means that, what about current density? Is it vector or scalar? Well, yeah, it's got to be a vector, so it is. It is a vector, which is a little bit weird, even though current is not a vector, current density is. I know that's really strange, right? So it's going to be a vector that's in the same direction as the drift velocity. Whichever way the charges are moving, that's the direction of the current density vector. So we can go ahead and put the vector arrow over the J in the equation and the J in our definition. There it is. So it is a vector quantity. All right, what about the units for current density? Yeah, we should be able to figure this out. Obviously, current is measured in amperes. Area in meter squared, so it is the ampere per meter squared. Okay, so let's just play around with the equation a little bit, see how we can relate it to other things we've been talking about. So I'm going to leave the bottom A, but the top, we're going to fill in the equation for current that we developed just recently in terms of drift velocity, which we said we're pretty much never going to use. Well, here it is again, the Nevda equation. And you can clearly see the area goes away, and we're left with this equation that the current density is related to the drift velocity. So here's a direct correlation showing that the direction of the drift velocity is also the direction of this current density. We can play with this a little bit more if we solve this equation for current. So it's going to be current equals current density times area. And technically, since we're multiplying two vectors, we have to know which way we're multiplying them. It turns out it happens to be a dot product. You wouldn't know that from the original equation, but there it is. That current is the dot product of the current density vector and the area vector. This looks a little familiar. We've seen other dot products that are like this, specifically when it deals with, maybe not current, but with something flowing from one place to another. Something else where there was a dot product of two vectors and got a scalar as an answer, that a scalar has something to do with like flowing. This might remind you of like flux, right? Electric flux was the dot product of electric field and an area vector. And gravitational flux was the dot product of gravitational field and the area vector. So we can sort of say that current is the flux of charges flowing. And so we're going to write this in a similar way to the way we've seen Gauss's law. It's not Gauss's law, but it takes on a similar form. That current is the surface integral of the current density dotted with a tiny infinitesimal bit of area, surface area, where this allows for the current to be different densities at different locations. If you imagine, like, an area here, we have a different density here, and here, and here, and here, and here in that cross-sectional area, and if you sum it all together, you get the full current flowing through the conductor. Fantastic. Okay, let's go back to the idea that we have this potential difference from the left side of the wire to the other, forcing positive charges this way, which means there's actually an electric field inside the wire. So just go ahead and draw an electric field line showing which way the field is pointing. Sure, it points from high to low. In fact, I'm going to draw two of these because if the current density is uniform, then we can sort of imagine this as having a uniform electric field within the wire. Almost as if there were oppositely charged parallel plates, a high potential plate here and a low potential plate there, creating a uniform electric field. We can then relate the field inside the wire to this idea of a uniform field between plates, where we know the equation for uniform field between plates is delta V over delta D. I put the absolute value there. We know it's really negative dVdr, but just, make it nice and easy. And what's the delta D? Well, from one end of the wire to the other, that's just going to be L, the length of the wire, so it's delta V over L. And we have a voltage source creating this potential difference, and protons are moving from one side of the wire to the other, and there's going to be a voltage drop from one end to the other. So Ohm's law tells us that voltage drop will be I times R, where R is the resistance of the wire. Remember, ideally wires shouldn't have resistance, but we know in the real world they do. And what's the equation for resistance of a wire? It's been a while. Oh yeah, R equals rho L over A. Now, in this equation for electric field, we have R over L. Here we have R and L. Let's just rearrange this so it says R over L. So put the L on the denominator there, and the other stuff's going to be on the right-hand side. We're left with this, that R over L equals rho over A. And where here's R over L, we're just going to replace that with rho over A. So we're left with this. The electric field is current times rho over A. Why is that useful? Well, what do we have here? Current over area, and that is current density. So putting it all together, we have this relationship, that electric field is rho times current density. Well, just to remind you, because it's kind of confusing, we are talking about density, you might be tempted to say, oh, rho, that's volume density. Well, it is in other contexts, but here, no. It had to do with the resistance of the wire. Rho is resistivity. And so here we can see that the current density is related to the electric field within the wire.